Hello again. We're up now to lecture 3, and we're going to talk a bit now about p-hacking, which many of you might have heard of. It's a really good thing to illustrate with simulations. So I'll share my screen again. Okay, p-hacking. It's known as other things. It's also referred to sometimes as data dredging or asterisk hunting. With the idea that people doing research often just look out for a significant p-value and get excited by it without really thinking about how it was arrived at. And I would say this is endemic in several fields of science, that people are using p-values as an indication of how important, exciting a result is without taking the context into account. And this is, I think, a reason for why we have a literature that's really full of false positive results and very misleading for that reason. Let's take a simple example. Suppose I've tested 16 compounds to see if they improve memory in rats. So this is what I see. These are the results I get. I've got my 16 compounds here along the bottom, A to P, and 2 of them are looking really exciting because they are significantly different from 0. This is a measure on the y-axis of memory improvement, and 0 would mean the compounds are not really doing anything, but these 2 look as if you might want to take them forward into further trials. So is that the case? It isn't, because what is going on here is p-hacking. And I'm going to try, first of all, to just give you a more conceptual explanation of it, but then I'm going to suggest that we look at this using simulation, because I think that gives you a much firmer grasp of what the problem is. But the conceptual explanation, you can use poker. Games of chance were very much how probability was first investigated. People started to get very interested in the mathematical properties of in games of chance of different card hands, for example. And we know that if you're playing poker, this is a hand called 3 of a kind, where 3 of your cards are the same, they're different suits, but the same value. And we know that that sort of hand, which is moderately valuable, comes up on about 1 in 50 draws just by chance, if you're taking an unbiased set of cards. Now, suppose I said, here's my friend, he's a magician, and by mere sort of power of thought, he can make the cards fall into that particular pattern well above that level. And so he comes along and he says he's going to deal you 3 of a kind just by thinking about it. And he's not cheating, he's got an unbiased deck of cards. In fact, you could be the person picking the cards. And you get really impressed because you get 3 of a kind. On the other hand, if you knew he'd gone all around the room trying out this on 50 different people, and just one of them got 3 of a kind, you wouldn't be impressed, at least you shouldn't be, because you'd realize that that's about what you'd expect just by chance. So I hope with this example, what I'm getting across is the idea that you could say, well, a three of a kind is an unusual hand, it's 1 in 50, but it's only meaningful if you know how many times he's actually tried. The surprisingness of that result is only interpretable if you know the full data set. In other words, if you know all the things this guy tried. The key error that is made all the time in many scientific disciplines is that the p-value is treated as an indicator of the importance of a finding, regardless of the context in which it was obtained. So these numbers that I showed you just now were actually obtained by a simulation of random data of just the kind that you have been simulating. And it just so happened in this particular run of the simulation that 2 of these popped up as having p-values less than 0.05. And you might think, well, that seems very high because we should only get 1 in 20. But the key point is you're not testing whether compound G or compound J is significant here, because the way this whole study has been set up is that the interest is in, are any of these 16 compounds having a good beneficial effect? And that's a different question that you're asking, which requires a different type of probability, because what you're really asking is, what's the probability that none of these compounds is significant? Because you're not bothered which one it is. You're just looking for something that passes this screen. And so the probability that none of them are going to pass the screen is actually 1 minus 0.95 to the power of 16. 0.95 is the likelihood, if there's nothing going on, that you will see nothing. So you take that to the power of 16, and that gives you the probability of 0.6. So the probability that something in this experiment comes out as less than 0.05 is as high as 60%. And yet we see time and time again people making this fundamental error of testing lots of things and not doing any kind of correction for the number of tests that they're doing, and thinking that nevertheless p less than 0.05 is meaningful. Now, I'm going to suggest you try and simulate this situation. So you can go back to your existing Excel sheet and you can just cut and paste the column with z-scores and the formula to generate these data to simulate many different compounds. So I'll just show you how to get going here. So here we are, I've got score. Well, you can just copy all of that, copy and paste, and if you've got a tidy mind, you might want to say, call them A, B, C, etc. And then you need to do, you've got this thing that they're all going to come out identical because we've got this fixed, but we now know that what we've got to do is this calculate now button. Here we go, there it is. And you can see different p-values for different compounds, but I'd like you to try that with going right across and doing 16 altogether. And get a sense of really just how frequently then you can get something less than 0.05 as the exercise. So this should bring home, I think, the point about the conjurer and the rest of it, and how critical this actually is to correct in some way for the number of tests that you are doing. But I'll stop there for the moment and let you try that out and return for the next lecture in a little minute.